Hello, everybody. Mr. Klein in the house. I'm here today to talk about something called a cumulative relative frequency graph. And since that is a mouthful, usually we just call it an ogive. Here's what it means. This right here is a cumulative relative frequency graph for a set of data describing the duration of eruptions of Old Faithful. Old Faithful is a geyser, and it is known for being very, very, very consistent about the time when it will erupt. I saw it once. I was about 7 years old. It's my attempt at drawing Old Faithful. Anyway, when it erupts for a certain amount of time. And so suppose we got a large data set, and that data is always going to be here on the x-axis. On the y-axis, what we do is we graph the percentile. So the values of the data are increasing in minutes from here until we move to here. And there's a couple things that are always going to be true. You're always going to start at 0. Okay, or at the 0th percentile. And right here, for the maximum value, you're always going to end at 1, or AKA 100%. All right, so let's take a look at these data. Why do we study these ogives? Well, they tell us some stuff. So let's look at some questions we can answer using this graph. You witness a 3.5-minute eruption. At what percentile is this eruption? Well, we could start with that 3.5 minutes. We'd come down here to the x-axis, and 3.5 minutes looks like it's right about there. What we do is we move vertically up to a point on the curve. Now, it doesn't have to be one of these little dots here. It could be any line on the curve. And then from there, we move across to the y-axis. And can you see that this is lining up with 0.4? So that means that a 3.5-minute eruption is at the 40th percentile. Or in other words, it's a little bit below average. Let's talk about a problem that goes in the other direction. How long is an eruption at the 80th percentile? Well, since it mentions percentile, we want to begin by coming over here where the percentiles are. And 80th percentile refers to 0.8. And so from there, I am going to track across to the curve. Looks like it's hitting right about here on the line. And so if I move my way down, that looks to me like it's a little bit closer to the 5 than to the 4. So we would say it's approximately 4.6 minutes in duration. Okay. Let's do one more together. What is the interquartile range of that should be eruption times? And so the interquartile range we know traps between the 25th and the 75th. It's the distance between those two. So what I would do is come over here, identify the 25th, and then identify the 75th. Now we are estimating a little bit, and then the 25th would correspond to, I'm going to say that's about 2.3 minutes. And the 75th would correspond to, that looks to me like it's about 4.3 minutes. So the interquartile range would be equal to 4.3 minus 2.3, which is going to give us 2 minutes. All right. So think of that as skill number 1. You should be able to look at and interpret one of these ogives. But there's more. Another thing that you want to be able to do is look at one of these ogives and interpret what the shape of the distribution is and think about what that tells us. Let's imagine that I've gathered some data, and that data represents the hours of sleep that students in this class get each night. Now we're going to look at 3 different possibilities for this graph, so get ready. Okay. Imagine first, suppose that I had already drawn a histogram of these data, and the histogram looked a little something like this. Okay, so a lot of people 5 to 6. You guys aren't sleeping enough. Fewer 6 to 7, even fewer 7 to 8, and then very few 8 to 9. So we've got this graph, and it is skewed left. Well, think about how this would translate into an ogive. You know that right here at 5 hours, since nobody's less than 5 down here, that 5 would correspond to the 0th percentile. And you also know that since nobody is greater than 9, 9 would correspond to the 100th percentile. Well, how would the lines go for the rest of the graph? Well, it looks like it's increasing the most greatly here, and then less greatly here, and then less greatly here, and then less greatly here. So this is going to be a rough graph, but you would expect that you would have a large increase, and then a smaller increase, and then a smaller increase, and then a smaller increase. So when you get this kind of concave down shape, you can assume that that is skewed left. And again, the way to think about it, I don't expect you to memorize this stuff, but the way to think about it is that the greatest rate of increase here corresponds to like the largest frequency or the highest bar in a histogram. All right, let's try another one. Imagine you have this time an ogive, and I tell you that the ogive has a small increase, followed by a large increase, followed by a large increase, followed by a small increase. So small, large, large, small. Not steep, 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 not steep. Well, if you were asked to sketch a histogram of this, I'm going to have a small bin, followed by a tall bin, followed by a tall bin, followed by a small bin. Not steep, 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 not steep. Small, tall, tall, small. Okay. So a graph like this one is going to be symmetric. Let's try one more. Let's suppose instead it had gone steep increase, small, small, steep increase. So the steep increases are at the beginning and at the end. What kind of graph would you have that this time? All right, well, let's see. I know that I would have tall bar, small bar, small bar, tall bar, which means that an ogive that looks something like this, where a lot of people are getting bad sleep and a lot of people are getting good sleep and not too many of us in the middle, this would be bimodal. All right, so there it is, ladies and gentlemen. You know what an ogive is, you know how to read an ogive, and you know how to relate the ogive to the shape of the distribution.